All right, guys, so I want to keep talking about the normal distribution and one last really interesting application of it. So let's take a look at this situation here. Let's say that we have a new cancer treatment, that cancer treatment has a 65% success rate. I'm going to ask two questions here. The first is, what shape is the probability distribution for a hospital with 10 cancer patients? And then how about a hospital network with 500 cancer patients? And so essentially what you have here is a binomial distribution, right? Why is it a binomial distribution? Well, first of all, we have fixed number of trials, right? We have 10 in the case of the hospital, and we have 500 in the case of the hospital network. We have a probability. So let's see, N is 10. And then we have N is 500, okay? And in each case, we have a probability of success being 0.65, right? And so what I'm going to do is I'm going to sneak over here to Microsoft Excel, and I want to check out these distributions with Excel. So let's, oh, come on, you guys need to see this share here. Sorry. Okay, so we've got n equals 10. Let's start with that example. And so I'm going to have my x, meaning my number of successes, and my probability of success, okay? Now, what are my possible values that are random variable? Let's think about this. Okay, I got 10 patients. Treatment could be successful for 0, or 1, or 2, or 3, all the way up to 10, right? So my values of x will be 0, 1, and so on. So I'm going to just kind of give myself some formatting here. All right, so I'm going to drag this down. Oops, one more. Okay, so there's my values of the random variable. Now, my probability, this is binomial, so I'm going to compute, right, my x will be, in this case, a 3, the number of trials is 10, and I don't want cumulative, right? I want the individual probabilities. So I'm going to call that false this time. And so what I have, too few arguments. Let's see, what did I do? Oh, probability of success. That might be helpful. What was my probability of success? Let's see here, 0.65. Okay, so 0.65, and then false. Okay, and so there's the probability of 0 successes. Okay, so this says if you had 10 patients, what's the probability that the treatment was successful for none of them? And then I'm just going to drag this down, and that will give me the other probabilities. Okay. The next thing I want to do, right, I want the shape of this. So I'm going to build sort of, not really a histogram, but I'm going to build kind of a bar graph here that will show me the shape. Okay. So I'm going to just kind of grab all this, and when I come back, we will have a nice bar graph. Okay, so there's the distribution shape for 10. And it looks normal-ish, right? It sort of kind of goes up here and then it comes back down. But let's see what happens when we get to 500. So now I'm going to say n equals 500. And I've got x, and I've got p of x. And going to, let's see here. Whoops, I want these centered. Okay, now I'm going to start at 0, and then equals, and I'm going to drag this all the way down. I need to get up to 500, right? So let's see. Oh, a little high. Take this down to 500. All right. And then I want my other column again to be, right, it's a probability distribution, so I should be able to see the probability for each one of these. And so this first one equals binom dist. Then the number comes from A22. This time I have 500 trials. Probability of success is still 0.65, and I want false because I don't want the cumulative probabilities. I want the individual probabilities. And now I'm going to drag this down.
200.
And so I'm going to get, all right. Now, when I build my chart, I want you to notice something. All right, so look at this distribution. This, if you had to name it, you would call this normal. And in fact, if this were displayed up on like a big like presentation board and you were sitting back a few rows, you probably couldn't even see space between this. You would guess that this is even continuous. And so something interesting happens here. When the sample size is big enough, this binomial distribution starts to look more and more normal. But we have to be careful because binomial distributions are for discrete data. Normal distributions are for continuous data. And so the question then becomes, can I use the normal distribution to approximate the binomial distribution? And of course, the answer is yes. And the conditions for that are as follows. We know that, so the conditions are that if NP and NQ are greater than or equal to 5, in other words, we have at least 5 successes and 5 failures, then the binomial distribution is approximately normal. And again, don't forget what our mean and our standard deviation are when we're talking about a binomial distribution. And so let's decide here if we can actually use that normal approximation. 17% of students drive a hybrid. You randomly select 20. So my probability is 0.17, and my N is 20. And so while I'm at it, let's get our Q as well, right? So if P is 0.17, then Q is 1 minus 0.17, which is actually 0.83. So NP is 20 times 0.17. Well, what is 20 times 0.17? Well, it's 3.4, which is not greater than or equal to 5. And so we may not use the normal approximation. Okay? We have to just stick with the binomial distribution. How about this one? 37% of dog owners have pure breeds. So there's my P, it's 0.37. My Q is going to be 0.63. And then my N is 65. Well, NP is 65 times 0.37. And is that greater than 5? Yeah, we can tell without even looking, right? So don't worry about what it actually equals. What I really care about is whether or not it's larger than 5. And you're welcome to compute it if you're not sure, but pretty sure here. And then NQ is going to be 65 times 0.63. Well, that 0.63, that's over a half. Half of 65 is much larger than 5, so I can already see that this is greater than or equal to 5. So in this case, yes. Okay? All right, but here's the problem. Binomial distributions are discrete, but the normal distribution is continuous. So if you think about wanting to find the probability that X equals a certain value, under the normal distribution, that would be 0. Because if you think about what the normal distribution does, you have to give it an interval, right? You have to say from here to here. Well, from some value to itself, there's no distance involved there. But under a binomial distribution, that's not necessarily zero. In fact, it usually won't be. So what do we do here? Well, here's the solution. Here's x equals k. Up here is the next possible value of the random variable. Again, remember, x is discrete. So after k, the next possibility is k plus 1. Just before k, the value would be k minus 1. And so what I'm going to do is I'm going to say the probability that x equals k, and this is from the binomial perspective, is approximately, and then watch this. I'm going to lengthen my interval. I want to trap k inside some interval. So I'm going to go from here to here. Notice that I've now got an interval, so I have length now, but I haven't widened my interval so much that I'm allowing for the possibility of the random variable being k minus 1 or k plus 1, okay? The only possible value under the binomial distribution that's contained in this interval is k, okay? So how far do I move? Well, 0.5 to the left and the right. So I'm really saying k minus 0.5 is less than x is less than k plus 0.5. And so that side of the equation is my normal distribution, okay? And we're saying that as long as we have at least 5 successes and failures, these two will be pretty close to each other, reasonably close to each other. Close enough that we can actually use this approximation. Okay, so let's put this and start putting this into practice. So the probability of getting between 11 and 15 successes inclusive. So I want to correct for continuity, right? I've got 11 and I've got 15. Now, if I'm talking about the binomial distribution, 12, 13, 14, then, right, I've got values before 11, possibly values before, after 15. And so from binomial, I want 11 less than or equal to x, less than or equal to 15. Well, here's the deal. 11 and 15 need to be included as possible values, right? Because it's less than or equal to. So I need to widen my interval, but not so much that I steal 10 or 16, right? I just want that 11 and 15 to be ever so slightly inside this bigger interval. So instead of starting at 11, we're going to start at 10.5. Again, there's that moving left and right by 0.5 units. And instead of stopping at 15, we're going to stop just a little bit past 15, but not so far that we get to 16. We're going to stop at 15.5, okay? So this side, again, is binomial. And this side is normal. And the interval that corrects for continuity is this right here, okay? All right. So here's some more examples. Determine the probability using the binomial distribution and then using the normal approximation. Compare the two probabilities. All right, so recent survey found that 20% of parents are unable to get the H1N1 vaccine for their child. You randomly select 150 parents. Now, first of all, let's do a quick check. Can we even use the normal approximation? Right, my P is 0.20. My Q is 0.80, and my N is 150. It's 20% and 80% respectively of 150 larger than 5? Yes, so we're good. All right, so binomial probability that exactly 45 say they are unable. Well, again, we're going to use that binom dist, or if you're using, I know some people might use like a TI calculator or something, it would be binom PDF. But I'm going to show you here with Excel. So binom dist. Okay, so equals binom dist. And then the number, well, we have 150 trials. I'm sorry, the number is 45, 45 successes. 150 trials. The probability of success is 0.20. And then cumulative, we're going to say false because we want exactly 45 successes. And so we get 0.0010. Equals 0.0010 if I go 4 decimal places. Now, let's take a look what happens if we use the normal distribution. Well, I need to correct for continuity, right? So I'm going to move left and right by 0.5. So I'm going to go from 44.5 to 45.5. And then use that norm dist, okay? Or if you're using one of the TI calculators, then you would use normal CDF, okay? But whichever one you use, you will get, and I'm going to just kind of give you the answer here. 0.0008, okay? So not bad, right? Pretty good approximation. That's within 2 10,000ths, okay? All right, how about the next one? Study found that 74% of adults prefer ice cream over frozen yogurt. That's good, some things are still right with the world. You randomly select 40 adults and ask if they prefer ice cream or yogurt. Probability that at least 28 prefer ice cream. Okay, so here, what I'm going to do is I'm going to use the normal distribution if I can. So NP is 28 times 0.74. That's greater than or equal to 5. NQ is 28 times 0. And then 1 minus 0.74, right? It's 0.26. This is also greater than or equal to 5. So we are good. We can use the normal distribution to approximate this. And so my correction for continuity, right? Let's see what we got. Correction for continuity. So under the binomial perspective, right, at least 28. So I need greater than or equal to 28. So I need to lengthen my interval just a little bit to put 28 properly inside the interval. Okay, I don't want my interval to start at 28. I want to put 28 inside. So my correction for continuity is going to be x greater than or equal to what? Yeah, 27.5. Okay. And so this is approximately probability and then go ahead and use the normal distribution. But remember, as you're using this normal distribution, I want to remind you that your mean, right, is n times p, and your standard deviation is the square root of npq. So I know I didn't mention that on the last example. If you're wondering how those numbers came about, well, this is your mean and standard deviation because you've got a binomial distribution, okay? And so whatever computational tool you use, Excel, or if you're using a TI or something, just put these inside the body of the argument, okay? So I'm gonna go grab what this turns out to be, and I will be right back. So we get 0.0017. All right. Last problem. A study found 35% of homeowners have solar panels on their home. You randomly select 10 homeowners and ask if their houses have solar panels. What is the probability that at least 4 homeowners have solar panels? So here we've got probability of at least 4. But can I use the normal distribution? Well, n times p, that's 10 times 0.35. That's 3.5, which is not greater than or equal to 5. So I cannot use the normal approximation. That doesn't mean this can't be solved, right? Remember, the normal approximation is used to approximate a probability distribution that we know quite well. But it's just in this case, I can't use the approximation. I have to use binomial. And so keep in mind how we find those greater than or equal to's, right? We use the notion of the complement. All right. So let's see what we get here. So whatever tool you use, right? Calculator or Excel, let's see what we actually wind up getting here. I'm going to go ahead and pause this and go grab the answer. So we wind up with 0.4862, okay? So I think a natural question is why? Well, if we have the binomial distribution and we have these computational tools that we can use, why would we want to approximate it with the normal approximation? And let me just offer this as a reason. Where we're going next is the very powerful part of the course known as Inferential Statistics. And this is where we start to make predictions about a population based on a sample. And in our analysis, sometimes we'll be looking at things that are inherently discrete, like the proportion of people that support a certain candidate for office or something. Right, you're counting. It's not a continuous distribution, but our analytic tools rely on the normal distribution because it's just so elegant, right? That beautiful bell-shaped curve with all of its wonderful symmetries. So what's going to happen is if the conditions are right for the normal approximation to be used, that's what we're going to use when we perform all these, whether it's hypothesis tests or confidence intervals, okay? So that's a reason for this little discussion about the normal approximation. We don't do it just because, hey, we can. We do it because it serves a purpose in the tools that we are going to use for making inferences. So you might just put this in your back pocket for now and say, okay, we're about to use it. It's really going to get used behind the scenes, but I don't want you to take anything for granted, really. I want you to have an idea of why we're doing what we're doing, and when conditions are given, why they're there to begin with and why they're necessary. So be familiar with this, the correction for continuity issue and all that. It's good to review. Obviously try some problems. And with that, I will just wish you guys a good day. See you soon.